Hello everyone. Welcome to the session on asset properties in RDBMS. In this session, we are going to understand how a database maintains the reliability of transactions. Now, before we begin, just think about a very common situation. Suppose one person is transferring money from one bank account to another bank account. Here, account A has 20,000 rupees and account B has 10,000 rupees, and a transfer of 5,000 rupees is being made. For us, it may look a simple transfer. We just enter the amount, click the transfer button, and wait for the success message. But internally, the database has to perform multiple operations correctly. So in this session, we will understand how the database ensures that the transaction is complete, valid, safe, and permanently stored. So these important characteristics are explained using four properties called the ACID, that is the asset properties. So asset stands for atomicity, consistency, isolation, and durability. So by the end of the session, you should be able to understand not only the definitions of these four properties, but also how each property works in a real world transaction. So before we go into the asset properties, we must first understand the meaning of the term transaction. A transaction is a logic unit of work that contains one or more database operations. Let us understand this using the example. Consider Anu has 20,000 rupees in her account and Ravi has 10,000 rupees in his account. So Anu wants to transfer 5,000 rupees to Ravi. Now, from the user's point of view, this appears to be one single action. But from the database point of view, several operations have to be performed. First, 5,000 rupees must be deducted from Anu's account. Second, the same 5,000 rupees must be credited to Ravi's account. So finally, the updated values must be saved in the database. So these are multiple operations, but together they form one complete transaction. Now, can we treat the debit operation and the credit operation as two unrelated updates? No, we cannot, right? So they are connected to each other. So if the database performs only the debit and does not perform the credit, the transaction becomes incorrect. So in an RDBMS, all the operations belonging to one transaction must be handled safely as a one single logic unit. This is exactly why we need this asset property. Now, the next question is, why do we need asset property? Why can't the database simply execute the operations one after another? The reason is that real world systems may face different kinds of problems. For example, what will happen if the server crashes after an amount is deducted from one account, that is, say, Anu's account, but before the amount is credited to Ravi's account? That would create a half completed transaction. Similarly, what will happen if a transaction produces invalid data? For instance, suppose a business rule says that the account balance should not become negative, but a transaction violates that rule. Another important issue is simultaneous access. In real systems, many users may access the same database at the same time. One user may transfer money, while another user may check the account balance or make another payment. So the database must handle all these simultaneous operations correctly, right? So one more problem is the data loss. Suppose the database displays a success message and immediately after that there is a power failure. When the system restarts, the completed transaction should still be available. So ACID properties protect the database from server crashes and invalid data, then simultaneous transactions and if any unexpected failure. That is why ACID properties not just a theoretical concept. It is one of the main reasons why users can trust systems such as banking applications, shopping websites, or ticket booking platforms, etc. So let us now look at the first property, which is the atomicity. Atomicity means that a transaction must be completed fully or it must not be happen at all. So in simple words, we can say all or nothing. Let us apply this to our bank transfer example. There are two important operations. The first operation is deducting 5,000 rupees from Anu's account. The second operation is crediting 5,000 rupees to Ravi's account. So now, if both operations are completed successfully, the database can commit the transaction. The term commit means that the changes are accepted and permanently saved. But let us assume that the amount is deducted from Anu's account and, and before crediting Ravi's account, if a server error occurs, should the database leave the transaction in that condition? No, right? So the database should reverse the changes made by the failed transaction. This process is called a rollback. So if the complete transaction is successful, the database performs a commit. If any important step fails, the database performs a rollback. So therefore, Atomicity protects the database from half-completed transactions. Let us take another simple example. Suppose we are placing an order on an e-commerce website. The payment is completed, but the order is not created. That is also an incomplete transaction, right? So atomicity ensures that either both payment and order creation happen successfully or neither of them should happen. So once again, atomicity means all operations must succeed together or all of them must be cancelled. That is a simple definition of atomicity. Then the second acid property is consistency. So consistency means that the transaction should take the database from one valid state to another valid state. Let us look at the value shown on the slide. Before the transaction, Anu has 20,000 rupees and Ravi has 10,000 rupees. So the total amount is 30,000 rupees. After transferring 5,000 rupees, Anu has 15,000 rupees and Ravi has 15,000 rupees. So no money has disappeared and no extra money has been created. The database remains in a valid state. This is one of the example of consistency. But consistency is not limited only to checking the total amount. So it also means that all the rules are and constraints defined in the database must remain valid. For example, suppose the bank system has a rule that the account balance should not become negative. So if Anu has only 3,000 rupees and tries to transfer 5,000 rupees, the transaction should not be allowed unless the bank provides an overdraft facility, right? So similarly, a primary key should remain unique and a foreign key should refer to a valid record and a compulsory field should not be left empty. So consistency ensures that the transaction does not violate the rules of the database. The third property is isolation. So isolation deals with multiple transactions happening at the same time. in the real world application, the database does not normally handle only one user. It may handle hundreds, thousands, or even millions of users. So multiple transactions may access the same data simultaneously. For example, transaction one is transferring 5,000 rupees from Anu's account to another, like Ravi's account. At the same time, transaction 2 may be checking Anu's balance or trying to make another payment. Now, while transaction 1 is still in progress and transaction 2 should not see incomplete or partial information. For example, it should not see that the amount has already been deducted from Anu's account while Ravi's account has not yet been credited. So that would be a wrong intermediate view. Instead, the second transaction should see a consistent result. So it may see the old balance before the transfer, or it may see the final balance after the transfer is completed, depending on the isolation level used by the database. But it should not see the incomplete changes of an ongoing transaction, right? So isolation keeps simultaneous transactions logically separate. It prevents one transaction from disturbing another transaction. So in simple meaning, the isolation, which is the transaction should not interfere with one another. That is called as an isolation. The fourth property is durability. So durability means that once the transaction is committed, its result must not be lost. Suppose the transfer from Anu to Ravi is completed successfully, the database commits the transaction and displays a success message. Immediately after that, there's a power failure. Now, when the system restarts, should the transaction disappear? Definitely not. So once the database confirms that the transaction is successful, the updated data must remain permanently stored. That is called durability. So the databases achieve durability using mechanisms such as transaction logs, stable storage, checkpoints, and some recovery procedures. So, for an introductory understanding, we do not have to go deeply into these mechanisms. We only need to remember the important point. So, a success message is meaningful only when the committed data survives even after a system failure. So, the simple meaning of durability is once committed, always stored. So now let us connect all of these four properties in one complete transaction flow. So the transaction begins first. Atomicity ensures that all the operations are completed together. If any important step fails, the transaction is rolled back. Next, the consistency ensures that the transaction does not violate any business rule, database constraint, or any integrity condition. So, isolation ensures that other transactions do not see incomplete changes while this transaction is in progress. So, finally, durability ensures that once the transaction is committed, the final result remains permanently stored. So all four properties work together. They are not independent features used separately. Together, they make the transaction reliable and trustworthy. So we can also connect these concepts with a few SQL transaction control statements. The first one is the begin transaction. This indicates the beginning of the transaction. The second one is the commit. Commit is used when all the operations are successful and the changes have to be permanently saved. And the third one is the rollback. Rollback is used when an error occurs and the changes made by the transaction have to be reversed. So now, one important point here is that these comments help us control transactions. But asset properties are supported internally by the complete database management system. So the comments alone do not represent the entire implementation of this asset property, but they help us understand how transaction control works. So far, we have used a banking transaction because it is easy to understand. But asset properties are required in many other applications as well. So we can say it can be used in the e-commerce order. So when a customer places an order, several operations may be involved. The payment should be confirmed, the stock quantity should be reduced, the order should be created. All these values should match. For example, the system should not accept the payment and then fail to create the order. The next example is railway or flight booking. So when a seat is booked, the payment and seat allocation should be properly connected. The system should also prevent two customers from booking the same seat. Another example is the hospital management system. So patient records, prescription, test results, and billing details must remain accurate. So the system should not say only a part of a medical update. Similarly, in the college fee portal, when a student pays the fee, the payment record, receipt generation, and fee status should all remain consistent. So, asset properties are useful wherever correctness, reliability, and trust are more important than simply storing data. So, you can also think of online wallets, hotel booking systems, insurance applications, and payroll systems. All these applications depend on reliable transactions. So let us quickly recap the four properties. A stands for atomicity. Atomicity means all or nothing. Either the complete transaction is successful or the complete transaction is rolled back. C stands for consistency. So consistency means the database moves from one valid state to another valid state. All the rules, constraints, and relationships must remain correct. I stands for isolation. Isolation means that simultaneous transactions should not interfere with one another. Other transactions should not see the incomplete changes of an ongoing transaction. And D stands for durability. Durability means that once a transaction is committed, its result remains permanently stored even if a failure occurs afterward. So one simple way to remember ACID is transactions must be complete, correct, separate, and permanent. So atomicity makes them complete, consistency makes them correct, isolation keeps them separate, and durability makes them permanent. So these four properties form the foundation for reliable transaction processing in an RDBMS. Thank you for listening. I hope the concept of asset properties is now clear.